Okay, so now I will tell you about spherical coordinates. In this video I will just explain what they are and how you would compute the volume element, and then in the next one I'll do an example. The idea of spherical coordinates is similar to how cylindrical coordinates were used. They're just a bit more complicated, maybe better suited for things involving spheres and really maybe ellipses, but that's ellipsoids, but that's basically it. So what's the point of spherical coordinates? You have a point x, y, z in space, okay? And now we want to specify this point. Instead of using x, y, and z, we want to specify this with three other coordinates. So a useful coordinate to use is the distance from this point to the origin, which, okay, sometimes this is called r, which is very natural because it's a radial distance, but for now, because this is what the book uses, I'll call it rho. Okay, and this is like the length of the position vector. So if you want to say it like this is the norm of the position vector. Which is, remember, x squared plus y squared plus z squared, and then you take the square root of that. Okay, so this is different from the distance that we were using in cylindrical coordinates, because the distance in cylindrical coordinates is always with respect to the z-axis at the same it's always the distance of this point to the z-axis, not from this point to the origin. Okay, and then the idea is more like specifying a point on the unit sphere where you would use latitude and longitude. So we're going to use an analog of latitude and longitude, which are given in terms of angles. So there will be, again, if you think of this as really specifying a position vector, let me just put like an arrow here. Then there's this angle, which I will call phi. Although sometimes I usage is different and you call this theta, but again I'll try to follow the conventions of the book. So phi is just the angle between position vector and the z-axis, or between, remember that the angle of the vector specifying the z-axis is like the one that we call k, which is 0, 0, 1. Angle between k and position vector. Okay, so we're going to keep track of this point using rho, phi, and we need a third coordinate because a number of coordinates needed to specify a point cannot change. So imagine that from this vector you create a shadow point, which is x, y, 0, so it's like a projection. And to this vector we can find the usual angle. We can take the usual angle from polar coordinates. Okay. And so theta is the usual So what would this transformation look like? Well, let's try to find what x, y, and z are in terms of these variables. Notice that you can move this segment up here, okay? And if you do that, then you get like a right triangle where one of the angles is phi and the hypotenuse is rho. So that tells you immediately that phi has to do, that z has to do with the cosine of phi. So you can say that is the adjacent side, so z equals rho cosine of phi. Then rho sine of phi would be the opposite side, so you get it here. And to this one is this is like the r of cylindrical coordinates. So if you want an intermediate step, is that r from cylindrical coordinates is rho sine of phi. This is the one from cylindrical. And so now that we know the r from cylindrical coordinates, you can say that x equals r cosine of theta as before, but r is rho sine of phi. So you can say that x is really rho sine of phi cosine of theta. I'll write this again so that you have more space. And y equals rho sine of theta, which is rho sine of phi cosine of theta. So, sorry, sine of theta. So let me rewrite this one more time. What I'm saying is that x equals rho sine of phi cosine of theta, and y equals rho sine of phi sine of theta, and z equals rho cosine of phi. And so basically the only one that involves cosine of phi is the last one, and y is the one that has the two signs, and the x has one sine and one cosine. So what's more interesting is to find the values that these variables take. And so, well, basically, rho is just a distance. This distance from the origin can be as big as you want. So rho is just some non-negative number. Theta is the same theta as in polar coordinates, so you can take theta to be between 0 and 2 pi if you like. The one that makes, which is more fun to find, is phi. So how do you find the values for phi? Let me draw this again from a slightly different perspective. So let me draw first a sphere. So any point x, y, z, right? Any point x, y, z belongs to the surface of some sphere. Which sphere? The sphere whose radius equals the distance of this point to the origin. So if this one has distance rho, you can imagine a sphere of radius rho, and this point will belong to the surface of that sphere. Okay. So when you imagine at this point, you can take a plane which is parallel to the xy plane, passing through this point, and that will cut the sphere into a circle. Okay. And depending on where the point is, you get different circles. Maybe you get, well, you can also get the equator as one of the circles. And so basically you can think of phi, so you can think of phi as specifying the height of these circles. So here's phi, but it's specifying the height using an angle. So here's phi. The point is when phi equals 0, will be a line along the x-axis, along the z-axis, and then phi starts dropping. Once phi equals pi over 4, you are around this part. Once you get to the equator, which is this circle, you get to pi over 2, and then you keep dropping and dropping. Maybe this is like 3 pi over 4, and then you get to the south pole, and south pole equals angle phi equals pi. Okay, and again, that's all that you need. You don't need to go you don't need to go beyond pi, because the phi is only being used to specify the height of the circle. So on this side, you're also you're at the same height as on this side. So basically what I'm trying to say is that you only need to imagine that phi goes from 0 to pi. Another way to say this is that the height has to do with c, but cosine of phi is like an even function. So having used like negative values of phi would not have given you like new heights. So that's why we stick here. And then the point is that we would like to do triple integrals of some function times dv over some volumetric region. And we have seen that dv can be written like dx dy dc or dy dx dc and other things. If you write this, dv is in cylindrical coordinates, it was like r dz dr d theta. And the point is that there's like a formula for dv in spherical coordinates, okay, which will be rho squared sine of phi d rho d phi d theta. Okay, so this is what this is saying is that a little piece of volume in spherical coordinates looks like this. And why is that? Well, I'll show you an animation in a moment, because drawing this is a bit more complicated on the board. But what you should think about this, at least for a moment, is that again, this always has to, you always need units of volume here. Two of the three variables in spherical coordinates have no dimensions, right? d phi and d rho. Sorry, d phi and d theta. So this have no dimensions. D rho has dimensions of length. To get something with volume, you need to compensate by adding a factor of area. The only thing that you could get with area using these three coordinates is a power of rho. So rho squared times the rho gives you units of volume. And then there's like this rescaling factor which involves sine of phi, which is what hopefully will become clear once I show you the animation. But again, I'll just explain why dv is this has this particular form, and then next video I'll do an example so that you see how we'll use this in practice. So now I'm going to explain to you how to compute the volume element using spherical coordinates. This one is a bit more tricky than the cylindrical case, so let me go a bit more slowly. Basically, we will follow a similar strategy as before. So again, in spherical coordinates, the coordinates are rho, theta, and phi. And you have to imagine that all of these are increased by very tiny amounts. So what I will do is actually compute first the area of this sort of parallelogram. It's not quite a parallelogram, but it's very close to being one. And so after we have the area of this side, what you start imagining is that you start moving this along this angle, and it strips out this volumetric region. So the entire volume will just be the area of this side times the length of this arc. Okay, so how do you compute the area of this parallelogram in quotes? Well, first you need to know the length of this segment, and again notice that what you should think of is that you had started with radius rho, which is here, and now you're increasing it by some amount d rho. So the length of this segment is just d rho, and for the area you basically need to multiply it by the length of this segment. But this is similar to the problem that we had before. This is like the length of an arc on a circle of radius rho and some angle, and this is the angle that you obtain by moving the angle phi by a tiny amount d phi. So basically this length is rho times d phi. So far what we know is that the area of this side is just rho times d rho times d phi. And so basically what's left is to compute the length of this arc. Okay? And now one way to think about it is that again there's a circle hidden in all of this discussion, but now you should think of a circle whose radius starts from the z-axis, okay, and whose angle, the angle of this circle, actually corresponds to the angle d theta downstairs. So it's a circle of radius, or an arc coming from a circle with angle d theta. And so what the only thing we have to figure out is the side, the length of this radius. But basically, as I explained before, that's just rho times sine of phi. So basically this length is, the length of this segment is rho times sine of phi, and so the entire volume is rho times sine of phi times this area, which was rho d rho d phi, and so you get that the volume the volume in spherical coordinates is rho squared sine of phi d rho d theta d phi.